Howdy, folks. Okay, so we are moving on to chapter 4. It's going to take 3 parts actually to get through chapter 4, but luckily I don't think they'll be too long. Okay, it's a little bit hard sometimes to gauge when you have an empty classroom. You don't. Or I should put it this way, when you have a classroom full of people, you can gauge people very easily, like, okay, they're getting this, move on, or no, this is time. So it's a little bit hard to time these things sometimes, but try to go a little bit quicker, actually. So in that vein, we are going to be talking about alkanes. Remember, alkanes are a subgroup of hydrocarbons. Hydrocarbons, just carbons and just hydrogens. Alkanes have no double bonds, no triple bonds, okay? Consequence of that, by the way, another way you could describe perhaps alkanes is you could say it's hydrocarbons where every carbon is sp3, okay? If a carbon is sp3, it necessarily has 4 bonds, okay? The first thing that we're going to be talking about, first we're going to talk about carbon-to-carbon bonds and the fact that they can spin freely if they are a single bond. But if they're a double bond, they cannot spin freely, okay? And that has to do with the fact that, I think actually I talked about this in chapter 1, I think. The classes that I'm teaching are just starting to meld together in my brain. Anyway, single bonds are hybridized orbitals that do something called head-to-head overlap. And when you have head-to-head overlap like this, 2 orbitals overlapping like that, they can turn and rotate and they don't sacrifice any overlap. They're still overlapping fine, the 2 electrons are still occupying those overlapping orbitals, all good. Okay, but pi bonds are orbitals, they're unhybridized p orbitals that nestle up next to each other. Okay, if those spin, the second just even 1 degree spin, they've lost a little bit of overlap. Okay, and if they were to even try to spin just 90 degrees, you'd get 0 overlap. So it actually, in a sense, if you think about it, spinning a double bond or a triple bond means you actually have to break the bond. Okay. All right, let's put some stuff on the board real quick. Purple. Okay, so chapter 4, alkanes. All right. Intro. Okay. Alkanes are hydrocarbons. Okay, so only C's and H's with no pi bonds. All carbons are sp3. As we're going to see, you can actually have cyclic alkanes. Alkanes include things that come around as rings, okay, as long as there's no pi bonds in those rings. If they're straight chain, they're all going to have the same format of molecular formula. Okay? If straight chain, okay, in other words, not cyclic, they will be CnH 2n plus 2. Okay. If you think about a straight chain, they're all CH2, 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 but the end ones have to be CH3. Okay, it needs sort of caps, so those end carbons have their 4 bonds. Okay. Nice way to sort of point this out is with isomers, right? Both of those, okay, are what are they? C5H12. Okay? 2 times 5 is 10, plus 2 more is 12. Okay. All right, category of alkanes can include cyclic structures. Okay. And the formula there, if it's only one ring, if it's multiple rings, then you can get different formulas, but if only one ring in your cyclic alkane, then you're looking at CnH2n. Now you don't need those caps because they wrap around and they complete that fourth bond by bonding to each other. Okay, so this one is cyclohexane, C6H12. This is cyclopentane. And in just a minute here, we're going to spend a little bit of time learning about how to name these compounds. Okay. All right. Since all single bonds, okay, otherwise known as sigma bonds, can spin freely. Okay, so so right there, those guys, that can spin around and around and around. If it's spun, you could actually take this bond here and it could spin down here. So you could actually end up drawing this guy like that. Okay. We tend to draw in zigzag for there's a reason behind that, but we'll get to that a little bit later in this chapter. Okay, so let's talk about how we name alkanes. And to teach naming alkanes, I mean, it's a bit involved. But once you know how to name alkanes, learning how to name the other functional groups are just variations of that. So in learning how to name alkanes, you've sort of done all the hard work of learning how to name compounds in general. All right, and two things about naming. So there are there's lots of different naming systems. Okay, you pick some medicine, oxycodone. Okay, oxycodone is a generic name. All right, there are brands. Okay, or yeah, I'm trying not to use the exact same example that I have in there. I know. Tylenol. Okay. The generic name of Tylenol is acetaminophen. Okay. Acetaminophen, you can buy Walmart acetaminophen, you can buy CVS acetaminophen, or you can buy Tylenol. Okay. Those are all trade names. Those are a company that's taken on the generic compound and is now selling it under their trade name. Okay. And those are good, and those are fine, and they're quick. Acetaminophen, it's a pretty complex structure. It's a nice quick way of saying what that compound is. Okay. But it is helpful and it is nice to have a naming system where you don't have to have ever looked at the compound. Okay. but if somebody told you the name, you could actually draw it. Okay, that's called a systematic name. And that's what we're going to spend a lot of our time on. And remember, way back in chapter 1, there's 10 million known organic compounds. You don't have to learn 10 million names. So it's nice to have a naming system that describes the structure itself. Okay. The systematic names that describe the structures, they can become a little cumbersome. They can become kind of long to describe them. Okay. Unless it's something that's going to be really famous, like acetaminophen, it's still important to have those systematic naming systems. Okay, and I feel this is maybe kind of one of the cool parts of this class is that now when you see chemical names, if it's not a type of functional group that we learned how to name in this class and stuff, at least you'll have some idea of what they're getting at with the name. Okay, all right. Sort of the field of how to name is called nomenclature. How to name. Okay. Intro. Right. Lots of naming styles, okay, each with advantages and disadvantages. Okay, all right, so let's look at this compound right here. All right, well, you may know that under, generic name is ibuprofen. How do you spell ibuprofen? Okay. The trade name is, there's lots of them. Motrin, Advil. Okay. Again, for something like ibuprofen, you would have to have the structure memorized. There is a systematic name. Okay. And that is 2 bracket 4 dash parenthesis 2 methyl propyl phenyl close bracket propanoic acid. Okay. All right. Generic or trade names have to memorize. Okay. Systematic can be tedious. But describes the structure. We won't learn how to name something quite that complicated. Do this. I mean, you certainly could, but we just don't want to waste time, too much time on learning how to name things. But if you learned how to name substituted benzenes of medium complexity, you would be able to look at the compound, having never seen it, and generate this name. Or, importantly, you could do the reverse. You could look at the name and then generate the structure. Okay? And for simpler alkanes and other functional groups, when we get to them, you're going to be able to do that. Okay? All right, so we're going to focus mostly on systematic. Okay. And even within systematic naming, there is, how do I put it? Shucks. Within systematic naming, there are sort of old styles and new style. Okay, and it would be kind of nice if we could. Okay, we're just going to learn new style, okay? Some of the classic old style, they're pretty efficient, so we actually incorporate some of that old style naming stuff into the new. But we mostly do it on new. It's called IUPAC, which was actually a convention that was held. I think it was a convention. Yeah, it was actually, way back when, where chemists from all over the world got together and decided, okay, these are the rules we're going to come up with for naming. They're somewhat arbitrary. They just had to pick rules and, okay, pick them and let's go with them. All right? Okay. All right, so in general, there are three main parts. Okay. There is the prefix. Okay. Plus the parent. Plus the suffix. Okay. When we go through, and one of the first things we're going to have to do when we are naming an alkane is sort of figure out what's the main chain, okay? And that's a little vague. I'll get to it, but I think it's a little bit intuitive, okay? You think of sort of identifying a main chain and then branches that come off, just like the branch of a tree, okay? You sort of have the main, the main branch. No. Let's call it the main tree, and then you have branches that come off. Okay, so you have to identify the main chain. The main chain is going to be described here in the parent. Okay, the branches is going to be described by the prefix. Okay, and what type of functional group? Because this is a general approach for all functional groups. What type of functional group is actually described by the suffix? Okay, in the case of alkanes, it's just going to be ANE. ANE means, oh, okay, this is an alkane. Okay? If you look at the ones I put up here earlier, cyclohexane, cyclopentane, okay? Butane, propane, etc., etc. All right? Okay, so this is what and where are the branches? Okay. We don't actually call them branches, we call them substituents. Okay. This describes the main chain. Okay. And there's a process for identifying and choosing, okay, this is the main chain. It's a very it's not just, oh, you gotta come up with something. It's very explicit. Okay. this describes the main functional group. Okay, for alkanes, A and E. Okay? All right. The first thing that we're going to do is figuring out that main chain. Okay? And it's going to be a process of looking for what I described. I think books describe it, I've forgotten how. I mean, I'm sure they describe it one way or another, but what I describe it as, and probably the book too, is the longest continuous chain. Okay? You can almost think of the carbons as like stepping stones. Okay? And you need to get from point A to point B on these stepping stones. Okay? But strangely, you need to find the longest path. Okay? And you can't back up. All right? So it's the longest continuous chain. All right? And I'll show you examples along the way, obviously. All right. No, it's okay. Process. 1. Find the longest continuous chain. Okay? Which I will abbreviate LCC, not Leeward Community College, but longest continuous chain, and circle. Okay? So if I were going to describe the process, I won't use stepping stones. I just made that up on the spot. You're welcome. All right. Start at each end. Okay, each end carbon, CH3. All right. And count off looking for the LCC. Okay? And it's sort of trial and error. Okay? So, you've got this big long molecule. Okay, I'll start there, and count. Sorry, 1, 2, 3, 4, and then it comes down here, 5, 6, 7, 8. Okay, it's 8 if I do that path. What if I start over here? Because I've got some stuff over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's a longer one. Okay? Once we identify the longer one, we're going to draw a circle around all the carbons, all 9 carbons or whatever it is, all the carbons involved in that longest continuous chain. All right. Some examples. Okay. And you get a little bit better at these with practice. All right, so let's start on this guy. And let's start here. 1, 2, 3, 4, 5, 6, 7. The sort of the most straightforward, blatant chain is this horizontal one. Okay, and that was 7. You might ask, well, what about starting there? How do you know which one? It doesn't matter, actually. In a situation like this, if there's symmetry where, it's 2 methyls that just split like that, okay, or if it was even, 2 more carbons, okay, it doesn't matter. So 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. It will generate the same name, whichever one of these ends you start. But let's see here. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So that's actually even longer. All right? Don't worry about which one do you start at. It doesn't matter at this point. It will in a minute. 1, 2, 3, 4, 5, 6, 7, 8. It's the same thing. So this is the longest continuous chain. And now let's circle it. I include that carbon. And notice as soon as I do, it cuts off branches. Those are substituents that are described in the prefix. Okay? I'm going to try it with this one. Try it. Pause it. Do it. Oh, I'm in the way. All right. 1, 2, 3, 4, 5, 6. But that's probably not the longest. Looks like there's longer. 1, 2, 3, 4, 5, 6, 7. Okay? What about 1, 2, 3, 4, 5, 6, 7, 8? Okay? What if I had gone, started down here like I just did and then gone to this guy? It's the same thing. Notice the symmetry there. Okay? It should be 8 again. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So, I draw a circle encapsulating all 8 carbons. All right? Okay. Note. The circle cuts pieces off. Okay. These are substituents. Okay. Occasionally, you can find more than one path, more than one distinct path. Okay. This would not be a distinct path. It's the same path, it just is how you cut off a 2-carbon piece. But you can come up to situations where, oh, I found one path and it gives me 8. I found another path that gives me 8. And those are very different paths. We have to have some rule. The convention, they had to come up with some rule. What do we do in that situation? Okay? And the rule that they came up with, and it actually has a good reason, is you look at these 2 paths, okay? And you look at the circle. So you've identified 2 possible paths. Have both of them there and then circle both of them. It may mean that you need to redraw perhaps so that you can really look at them. Necessarily, after you draw that circle of those 2 distinct different paths, okay, one will have created more branches, more substituents, and one will have created less. You choose the one that creates more substituents. Okay? If there is more than one LCC, okay, pick the one that creates more substituents. Okay? All right. So if you go through our process here, 1, 2, 3, 4, 5, 6, okay? 1, 2, 3, 4, 5, 6, all right? And whether I go left or right, you can double check, 1, 2, 3, 4, 5, nope, okay, so 1, 2, 3, 4, 5, 6, or this just complete horizontal one, okay? So I've redrawn the same molecule twice so that I can really clearly show you the two different paths. All right, so there you go. Or we could have gone up here. Okay. In each case, I have encircled, what is it, 6 carbons, right? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, okay. 6 carbon. All right. Now, how many substituents did each circle create? This created 2 substituents. Oops. Okay. This created 1 branch, 2 branch, 3. So this is the one you choose. That would be the correct circle to go by. All right? Okay. We're now going to assign, once we've created our circle, and we know we got the right circle if there was a choice to be made, once we have the circle, we can actually create the parent. Okay? And the suffix, actually. Okay, so we're kind of most of the way there. To name the parent, the name needs to describe how many carbons are in that main chain. Okay, and we use how do I want to put this? Oh yeah, they're called root names. Okay, so we need a root name. All right, and the root names that we use are meth, eth, prop, but, pent, hext, hept, oct, non, dec, undec, dodec. Most of those are Greek roots. There is a few of them, I forget which ones are Latin. Okay, they are not unique. We have them in society, right? The Pentagon, okay, where our military, the head of our military is. That is a building that has 5 corners to it. Pent, 5. What's a good example? Hexagon, right? So forth and so on. Hex meaning 6. Okay. All right. So, oh, and then the suffix part. I think I described it actually at the very end of this description here, but the suffix part is just the functional group. We already know this is alkanes, so it's just ANE. Okay. So these, or this one, I should say, which is the correct one. All right. It has 6 in it, so this is going to be a hexane. Hex is 6, and ANE means alkane. All right. Okay. This here. So, or step 2. All right. Assign parent name. Okay, which is the main chain based on IUPAC. That's the convention, international, I have no idea anymore. Root names. Okay. Actually, rattle them off real quickly, but let me create a chart for you. Okay. All right. Okay, so number main chain. Right. Root name. Alright? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? This is meth. Okay? This is F. Okay? Methane. That's what comes out of cows' butts. Oh, shucks. Why did I put the A-N-E? I was thinking it. Prop for propane, like in our barbecues. Bute, pent, hex, hept, oct, known, deck, deck, do, deck. Okay. You can name ones that have no substituents, and then all you need is your root and your ANE ending. Okay? Octane, like we gauge the quality of gasoline, is just 8 carbons, straight chain, no substituents, octane. Okay. I already taught butane. That's a 4-carbon chain that's in cigarette lighters. All right. Red, hard to go. All right. Oh, okay. Yeah, so I've already described this, but I need to include in our procedure adding the functional group end. Okay, so 3, add functional group ending, okay, otherwise known as the suffix. Okay. For alkanes, it's A-N-E. Okay. If no substituents, okay, no branches, you're done. Okay? So, CH4 is meth, because 1 carbon, ane. Shucks. CH3, 2, so it's F, ane. Okay. That's 3 carbons, propane. Okay. All right. If you have different functional groups, you'll change that ANE ending. If it's an alkene, double bond, the ane becomes ene. Okay? You know things like polypropylene. Those are polymers that are made from a 3-carbon segment from this alkene, actually. Polypropylene is made from that. Okay? All right. Next thing we have to do, now we got to deal with the substituents. Okay? And we need to be able to say where the substituents hit the main chain. Okay? So the first thing we're actually going to do is take that main chain and we need to be able to number it. Okay? And you always have 2 choices. You know, you have this end, and you know, any main chain that you've encircled has 2 ends. You got to decide which one is going to be 1. All right? That's the whole task in terms of numbering. All right? And so we need some rule, and it's arbitrary, but we needed a rule that the whole world agrees on. Set the convention. Doesn't that sound like an exciting convention, by the way? travel all the way to some awesome European city and then sit in a hotel conference room and talk about naming organic structures. Does sound awesome. Yeah, so how are we going to number them? All right. What you want to do is look at the two chains, or the two ways you can number it, the two ends, that's what I meant to say, the two ends, okay? And start numbering 1, 2, 3, and the one that has a substituent, the first substituent, come at the lowest number, that's the correct way to do it. Okay? So if I start on say this side and I go 1, 2, 3, there's a branch, there's a substituent. Okay? But if I come here and I go 1, 2, and there's a branch, that's the better one. Pick the one where it comes at the earlier one. You might think, and it can happen, what if it's a tie? Oh, if I come from this side, 1, 2, there's a branch, a substituent. 1, 2, from this one there's it's at 2. Okay? Then you go by where does the second substituent come. Okay? All right. So our next step in our procedure, number main chain, okay, in the direction that first substituent comes at the lowest number. All right. Okay. Sorry. Okay. All right. So let's figure out our longest continuous chain. This one's pretty straightforward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That looks like the best, but let's always double check. Okay. 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5, 6, 7, 8. No, it's this long horizontal one. Again, it doesn't matter if I had started from there. Let's circle that one just for kicks. Okay. Make sure you get all the carbons. All right. Okay, now there's two ends. I could number it from here, I could number it from there. All right. Let's number it from there in purple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Let's do, is that picture going to be too crazy? Well, the first substituent comes at 2, right? Had I started at this end, 1, 2, 3, nah. Okay? That's the correct end to do it because the first substituent comes at 2. Okay? All right. So now we know where the substituents come, and where they come is actually going to be part of the name. So that first substituent comes at 1 will be part of the substituent name, and that is indeed our next task. We have to name the substituents. Okay? What you do to name the substituents is you again count how many carbons are in the substituent. There's 2, there's 1, there's 1. Okay? And you use those same root endings, meth, eth, prop, but, bent, hex, hep, doc, non, dec, undec, dodec. Okay? But rather than put A-N-E, all right, because it's a substituent, to distinguish it as a substituent, you put YL. Okay? 1 carbon, that's methyl. 2 carbon, that's ethyl. Ethyl. 1 carbon again, ethyl. Propyl, butyl, pentyl. Okay? So forth and so on. Sorry, got it. Write the name and position. Okay. Of the substituents. Okay. On structure. What does that mean? When you guys are starting out, what I suggest is you come over here and put the name, write the name on the structure, okay? You know, if this was a quiz or something or a final, there might be a line down here that says, what's the name? Put the name, all right? Put the substituent names up there so that you can see them and keep it all straight. That's my recommendation. Up to you. To name the substituents, okay, use the IUPAC group name. For number of C's, number of carbons, and add YL to the end. All right. There are some branches that you could break off, okay? And the branches have branches, all right? And then it gets, and there's a whole system for, okay, now you come up with a little circle of the branch, and stuff. That's way complex. We're not going to get into that. But for the simpler substituents that do have a little bit of split branching themselves, okay, there are some classic names, and this is a good example of where the old classic names are actually pretty helpful, okay? That we could just name the whole thing rather than branches here and stuff like that. We can name the whole thing as isopropyl, T-butyl, sec-butyl. Okay? Those are actually the three. Those are the 3 you need to memorize for this class. Okay. All right. So. Classic. Classic is not the word. Common names. Common names is the way we describe sort of the older system that still has some utility and still is used a bit here and there. There's some common substituents. Okay. With specific names. Okay. All right, so all right, this part is the main chain, okay? So this would be 3 carbons off the main chain, okay? But rather than it connecting to the main chain on one of the end guys, okay? So this is a propyl. It connects by the middle carbon of that propyl. This is called an isopropyl. Isopropyl alcohol, rubbing alcohol, maybe in your home right now. That has that little component and then actually just an OH right there. Okay, but again, we're doing it in the context that this is a substituent that's off the main chain. Okay. All right. What if you have butyl piece, all right? But it doesn't connect to the end. It connects to a carbon, the second carbon in on your butyl chain, okay? Doesn't matter whether it's that one or that one, and it's the same thing, all right? This guy is known as sec-butyl. Okay? And that is sometimes abbreviated just as S-butyl. Either is okay. Okay. All right. And then what if we have all right, this again, this is 4 carbons, 1, 2, 3, 4, and it's connected to the main chain, okay? But they're not in a row, okay? They are, all the carbons are connected to one central carbon. This is tert butyl, okay? Which is also sometimes referred to as T-butyl. The reason, by the way, for these names, remember primary, secondary, tertiary, quaternary classification of carbons? If you look at, you ignore the main chain, you just look at that carbon, okay? That carbon is connected to 2 other carbons. It's a secondary carbon, okay? This carbon, again, ignoring the connection to the main chain. It's a little bit confusing that way. Ignoring the connection to the main chain, this carbon is connected to 3 other carbons. 1, 2, 3. Tertiary. Okay. All right, we are almost ready to name this puppy. All right. So all we need to do, we know how to do our root and our parent and our suffix. Now we need to know how to do our prefix. We got to put all these substituents in the very front. Okay. The only thing you got to do is you have to decide in what order do I put them in. All right. Turns out you put them in alphabetical order, okay? So butyl, if there was a butyl and a propyl, you put the butyl first. Oh, okay, so it's 3 butyl, and then 7 propyl, okay? Little note I want to make right here is that when you are, so you gotta alphabetize your substituents. When you alphabetize your substituents, as long as they're not these common 3, you just use the first letter, okay? B for but, M for meth, P for prop, etc., etc. These guys, this doesn't play into the alphabetizing. That's how you alphabetize it. That's how you alphabetize it. This one, just to be a pain in the butt, that's how you alphabetize it. You do go by, the part that describes its shape, the I of iso. Okay? All right. So, step 6. Add substituent names, okay, in front of parent, okay, in alpha order. Okay. You don't put a lot of spaces, actually. Might be counterintuitive. If you have numbers that are mixed in there, 2 methyl, 5 ethyl, 8, you use dashes to separate numbers and letters. Okay. So dashes separate numbers, words, otherwise there's no space. This is definitely something, I mean, all of this stuff is, it's not that complex. These rules, this is a great example of it. These rules are not that hard. No harder than the rules of football, the rules of, my son's getting into these games, Clash of Clans, I don't let him play that one, but Clash Royale, or Royal Clash, Brawl Brothers, these things on the phone, he's playing some guy in Nigeria or something like that. I don't understand it, okay? He understands it. He understands the different rules of doing this. And so, I mean, the complexity of the things we're trying to learn here in organic chemistry are not that bad. They really aren't, okay? There's just a lot of them, okay? How are you going to put it in your head? How are you going to keep all this straight? Reps, okay? You put these notes on your paper, you read these notes 3 times. If 3 times is enough, you read it 5 times, all right? And you work efficiently, you work quickly, all right? You don't want to, you can come up with the greatest process, but if it takes you 8 hours every single day, it's not a good process. You gotta be efficient and quick, all right? My trade for being efficient and quick? Caffeine. I shouldn't be pushing caffeine so much, but yeah, it's pretty helpful. All right. So let's do a big old example. Okay, so name this compound. Okay, try that guy. Find the longest continuous chain, number the chain, name the substituents on the structure is my suggestion. Put it all together, putting the substituents in alphabetical. Okay, all right. Longest continuous chain, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, let's double check. That looks like the best. What if we started up here? 1, 2, this is actually symmetry right here, so turns out it makes no difference, but let's convince ourselves. Okay. Oh, no, it's not symmetry. I'm sorry, that's a lie. So what did I say? 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is definitely distinct. Okay, is there another one? What if we started here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope. It's the simple horizontal one. I keep on, in my examples where I'm explaining, further concepts, I often make the horizontal one the longest continuous chain, but it's not always the case. Sometimes the windy path is the longest continuous chain. All right, but here's our longest continuous chain. All right. Now we need to number it, okay? Start it here, start it there. Which one should we start at? This guy, because the first substituent will come at carbon 2. Here it will come at carbon 5. All right, so 1, 2, 3, 4. Sometimes students just weirdly skip 1. 6, and then 7. Don't skip any. Okay? Be methodical. All right, beautiful. Now we can name these substituents actually on our structure. Okay? Well, this guy here, he's on 2, so it's going to be 2, it's 1 carbon, methyl, okay? Here is one of the common ones, all right? So that is going to be 4 isopropyl, okay? This guy, this is where you've got 4 carbons and they all branch off one center one. This is going to be 7-T-butyl. Okay. All right. So now we put them in alphabetical order. Which ones are we going to alphabetize off? We're going to alphabetize off that, and that, and that. All right. So our first one is going to be this one. B comes before all that, so it's going to be 7 T. Beautiful. You don't put a lot of spaces in. It's a little bit strange. You do anytime you have a number or you have one of these little dudes. You do use dashes. So I'm going to put a number in here for the isopropyl. So I'll go dash for isopropyl. Okay. Dash 2 dash methyl. Okay. And 9 carbons is undec. And it's ANE because it's an alkane. Woo! It's a long one. Okay. And again, you know, you could be given that and say, hey, what's the name? Or you could be given the name, and that's almost easier. Is actually, you know, reverse engineering this to the structure. Okay. All right. Every once in a while, you might. What if we, especially methyls seems like a lot, but you can get others. Yeah, you might have more than one of the exact same type of substituent at different places on the molecule. Okay, and it would get tedious if you said 2-methyl, 4-methyl, 5-methyl. Okay, so what you can do is you can create a way of describing, well, how many methyls are there? Okay, and so what you're going to use is di, tri, tetra. So di is 2, tri is 3, tricycle, tetra, penta, hexa. Okay. So it overlaps with that IUPAC root system, but some of it's distinct. Okay. We use di instead of F for 2. All right. And then we just have to list where they come at. Okay. 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 So put some words to that idea. If more than one of the same type of substituent, okay? First thing you do is you got to give the positions. Give the positions where they are. Okay. So we would do that. You know, let's say they came. It was methyls, and they came at the 2 and 5 carbons on the main chain. You would go 2, 5 dash, and then you put dimethyl. Okay. Use di, tri, tetra, penta. Okay. So that's if there's 2, that's if there's 3, that's if there's 4, that's if there's 5. You don't see a lot of compounds, at least in our class here, that have more than that. All right. Let's do a big, crazy, hairy example. And I've given you all the pieces. Now let's see, you guys, put it all together. Okay. This thing is, it's going to be just a spiral web of carbons. Name that dude. All right, let's do it together. Let's find the longest continuous chain. Well, it's probably not this simple horizontal one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's better. So What about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? 10. Okay. That might be it, but let's double check here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope. There to there. All right. So. Once you establish that, it can be tedious, but you've done a lot of your hard work. The next thing we need to do is we need to number it. Do we number it from that end, or do we number it from that end? If we start here, our first substituent comes at 2. If we start here, our first substituent comes at 4. All right, so we start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now you just name your substituents. All right, so that's a 2-methyl. This is a ethyl, so that's 3-ethyl. Remember what this one is? It's 4 carbons, connects to the main chain by one of the middle carbons. So that is sec-butyl. Okay, that's a 7-methyl. All right, and we're done. Okay, so what we alphabetize by? Mostly it's just the first letter. Okay, so butyl is going to come first again. This is a 10-carbon chain, so it's going to be a decane. All right, so sec-butyl. Okay, what comes next are the ethyls, or the ethyl, sorry. 3 dash ethyl. Okay. Now we've got 2 methyls. All right, so we put in the positions 2, 7 dash dimethyl, because there's 2 of them, and we're done, except for decade. Look crazy, but in the end, if you just do it very systematically, not too bad. All right. One thing I want to go over is in this chapter, not just in this chapter, but one thing I want to go over as part of this chapter is what if your alkane has a halogen? Technically, it would no longer be just a plain old alkane, it would be an alkyl halide. Okay, but I still want to teach you how to name that within this chapter. All right, and it's not too hard. We've got our halogens, so fluorine, chlorine, bromine, and iodine. All right, you take the first part of it, and rather than have the INE ending, okay, you have so fluorine becomes fluoro. Chlorine becomes chloro, bromine becomes bromo, and iodine becomes iodo. Okay. And you would name them, F for, or you would alphabetize them: F for fluorine, C for chloro, or F for fluoro, C for chloro, B for bromo, etc. If substituent is a halogen, okay, remove IDE, fluoride, chloride, bromide, iodide, from the end, and add O. Okay, so, I don't know what I put in either. Normally you put, well, yeah, shoot. I mean, it depends what part. You've learned that if fluorine, yeah, really I should change this, sorry. fluorine, bromine, chlorine. Okay. The IDE is if it's part of a salt. I don't know why I put that in there. So you're removing the ine. Okay. So fluorine, or you're removing the ene. Fluorine becomes fluoro. Chloro. Bromo. Iodo. Okay? That's it, guys, for part one. I'll see you soon.